At cruising altitude, the Concorde fuselage stretched by up to 25 centimeters every single flight. The metal expanded because aerodynamic heating pushed the entire airframe to 127 degrees Celsius. Engineers accounted for this growth in every panel gap, door seal, and fuel line fitting. This was not a flaw they lived with. It was the price of flying at twice the speed of sound, and every part of the aircraft was designed specifically around it. At subsonic speeds, an aircraft pushes air out of its way. The air has time to move aside before the aircraft arrives. At supersonic speeds, the aircraft is moving faster than the pressure waves that would normally warn the air to part. The air cannot move in time. Instead, a shock wave forms, a thin boundary where pressure, temperature, and density all change instantaneously. Crossing the sound barrier is not a moment of sensation, it is a regime change. Above Mach 1, the physics of flight operate by different rules. Lift works differently. Drag works differently. The position of the aerodynamic center, the point around which all lift forces act, moves backward along the fuselage as the aircraft accelerates past Mach 1. This single effect is the defining challenge of supersonic transport. An aircraft balanced and stable at subsonic speed becomes dangerously unstable the moment it goes supersonic. Every design decision on Concorde was a direct response to that shift. A conventional swept wing works well at subsonic speeds. At supersonic cruise, its performance degrades rapidly. Drag increases, efficiency collapses, and stability becomes unpredictable. Concorde's designers chose a fundamentally different shape, an ogival delta wing. The term describes a double-curved triangular form, mathematically derived from the cross-section of half a cone. At subsonic speeds, this wing generated lift through vortices that rolled along the leading edge, controlled spirals of low pressure that kept the aircraft flying even at the steep angles required for takeoff and landing. At supersonic cruise, the same wing became aerodynamically efficient in a way no conventional swept wing could match. The thin, highly swept leading edge reduced wave drag, and the wing's geometry moved the aerodynamic center rearward in a controlled, predictable manner. No other production aircraft has used this technique before or since. The delta wing solved the stability shift simultaneously at both ends of the speed range, which is why Concorde needed no conventional horizontal tail. The 4 Olympus 593 engines on Concorde were extraordinary machines, but they had a fundamental limitation. They could not ingest air at Mach 2. Jet combustion requires subsonic airflow inside the engine. At 2,000 kilometers per hour, the incoming air had to be slowed before it reached the combustion chamber, and it had to be done efficiently, or the energy lost in the process would destroy the aircraft's range. Each engine intake contained a system of movable ramps. As the aircraft accelerated, these ramps angled precisely to create a controlled series of shockwaves inside the intake duct. Each shockwave slowed the air slightly. Across the full intake, the air went from Mach 2 at the inlet to subsonic at the engine face. The pressure recovered during this process was enormous. On some flight conditions, the intake compression contributed more thermodynamic work than the engines themselves. The intake efficiency was the single largest variable in Concorde's fuel consumption, and a malfunction in one ramp would immediately force a reduction in cruise speed. As Concorde accelerated through the sound barrier, the aerodynamic center shifted backward by a significant margin. If the aircraft's center of gravity did not also shift backward at the same rate, the nose would pitch down with a force the elevons could not counteract. The solution was to use the fuel load as a continuous trim system. Transfer pumps moved thousands of liters of fuel between forward and rear tanks as the aircraft accelerated. During the climb through Mach 1, fuel flowed toward the rear. At supersonic cruise, the rear trim tanks carried a substantial portion of the total fuel load. During descent and deceleration back below Mach 1, the process reversed, and fuel moved forward again to restore subsonic balance. The system was automated and continuous throughout the flight. If the transfer system failed at supersonic cruise altitude, the aircraft would go out of trim almost immediately. Pilots could handle it manually for a short period, but sustained supersonic flight without the transfer system was not possible. The fuel was not just propellant, it was structural ballast. Aluminium alloys lose a significant portion of their structural strength when held above 120 degrees Celsius for extended periods. Concorde cruised at exactly that temperature across its entire airframe, every day, for the duration of every supersonic sector. The engineers at Aerospace and British Aircraft Corporation specified a particular aluminium alloy, designated RR58, that retained its properties at elevated temperature better than conventional aerospace aluminium. The leading edges and nose ran even hotter. The nose itself had to droop for takeoff and landing. At rest on the ground, a fixed nose at the cruise angle would have blocked the pilot's forward sightlines entirely. At cruise, it was rigid and fully exposed to the aerodynamic heating. The 25-centimeter lengthening of the fuselage was not evenly distributed. The majority occurred in the forward and mid-sections. Engineers designed variable clearance gaps into the structure and used flexible seals throughout to accommodate the movement. The aircraft that landed was physically a different size from the aircraft that took off. Concorde was not an aircraft adapted for supersonic flight. It was an aircraft built entirely around what supersonic flight does to metal, to air, and to physics. The stretching fuselage was not incidental. It was the proof.